Alright, so this is Partial Fractions Decomposition, ION, Part 2. Now, we will be using this for integration, but I'm not really going to go over the integration part, because that's basic. Right now, I'm just going to go over the Partial Fractions Decomposition part. Alright? So, say they wanted you to integrate this. So let's focus on our integrand. So our integrand in this case is 5x squared plus 20x plus 6, all over x cubed plus 2x squared plus x. So this is a pretty complicated looking integrand. We can't do u substitution because the derivative of our bottom is not in our top, or the derivative of our top is certainly not in our bottom. So that won't work. And no real obvious kind of integrand manipulation will seem to work right off the bat. So we're going to try some partial fractions decomposition. Now it meets our first requirement of our numerator having a degree less, which in this case is 2, than our denominator, which in this case is 3. But we need to be able to see this bottom as a product of, we need to factor it as a product of a series of terms. So let's just break this down. So this rational function integrand can be rewritten as 5x squared plus 20x plus 6 over, well, there's an x in everything, so let's factor an x out. X times x squared, take an x out, plus 2x, take an x out, plus 1. Okay, well, hey, we can simplify that. X squared plus 2x plus 1, that's pretty simple. That's 5x squared plus 20x plus 6 over x times x plus 1 squared. Okay? Now this is a repeated linear term in the denominator, which means we have a special rule we need to follow when doing our decomposition. So we're going to say, like in our previous video, that there are numbers a, b, and c that allow us to do this, where a over the first factor of our denominator, which is x, plus b over the second factor, which would be x plus 1, plus c over our third factor. Well, what's our third factor? It's technically x plus 1 again, right? Because x plus 1 times x plus 1 squared, so that's times x plus 1. But we can't just make this c over x plus 1, because then these two fractions would have the same denominator, and then we could just combine them, and then we'd have just a and b. So two constants, and that would misrepresent this function here. So that would create inaccurate values for a and b. So instead of x plus 1, we're going to put x plus 1 squared. Alright? So after that, everything is exactly the same. So let's just try walk through it. So we would have to multiply, to get our first a term, to have this denominator of x times x plus 1 squared, we'd have to multiply it by x plus 1 squared on the top and bottom, right? So x plus 1 squared over x times x plus 1 squared. Plus b, we'd have to multiply this by x, and then another x plus 1, so we'll have x times x plus 1 squared. So times x, and then times x plus 1. All times x plus 1 squared. Plus c, well, to give this a denominator of x times x plus 1 squared, the only thing it doesn't have is just that extra x on the outside. We'll just multiply it by x over x. Alright? And now they all have common denominators, so now we can add them up. So we'll have a x plus 1 squared plus bx times x plus 1 plus cx all over x times x plus 1 squared. Now this, we said was equal, if this is equal to this, and we've just shown algebraic steps to show that this is equal to this, we know that this is equal to this. So we'll have 5x squared plus 20x plus 6 over x times x plus 1 squared. So just like in our basic decomposition, we have common denominators, so we can just cancel them out. So we're left with 5x squared plus 20x plus 6 equals a times x plus 1 squared plus bx times x plus 1 plus cx. Alright? So now, just like our other video, we're going to pick convenient values for x so that we can solve for a, b, and c. So one obvious convenient value for x would be 0. Because if x equals 0, we'd have c times 0, so c would disappear. We'd have b times 0 times whatever, but the main thing is we'd have b times 0, so b would disappear. So then we just have a. So let's try where x equals 0. So if x equals 0, we'll have 5 times 0, so that's 0, plus 20 times 0, so that's 0. So I have 6 equals a times 0 plus 1, that's 1 squared, so that's just 1, so a times 1 is a, plus, well, if x equals 0, we'll have b times 0, so this will be 0, so, and c times 0, so this will be 0. So really, we just have 6 equals a. Pretty convenient. It's a good convenient value for x. So let's try another convenient value. So another convenient value we could use would be x equals negative 1. Equals negative 1. Why would that be convenient? Because if x equals negative 1, this term becomes 0. X plus 1 equals 0. So then our a term will equal 0. So that'll disappear our a. And then x plus 1 here, that'll be 0 too. So that'll disappear our b. So then we'll just be left with c. So if x equals negative 1, we'll have 5 times negative 1 squared, so that's 5 times 1, so that's 5, plus b times negative 1, that's negative 20, or sorry, 20 times negative 1, so that's negative 20, plus 6 equals a times, so if x equals negative 1, this will be 0, so 0 squared is 0, and a times 0 is 0, so we can ignore that. And then b times negative 1 times x plus 1, well, x plus 1 is 0, so this whole thing will be 0 too, plus c times negative 1. So we're left with b minus 20, so that's negative 15, plus 6, so that'll be negative 9, equals negative c. So 9 equals c. Okay? Now, there's no convenient value we could give b, or that we could give x, to make just a and c disappear and solve for b. So what we have to do then is plug in our value for a, and plug in our value for c, and then pick another convenient value for x, and then solve for b. So usually a good convenient value for x is 1. Right? It's easy to do math with 1. So let's try it. So 5 times 1 squared, well that's just 5, plus 20 times 1, that's just 20, plus 6, equals a, well that's 6, times 1 plus 1 is 2. 2 squared is 4. So we'll have 6 times 4, plus b, so that's what we're trying to solve for, b times, well, x equals 1, and x plus 1, that's 1 plus 1, so that'd be 2, plus c times x, and x equals 1, and c equals 9, and x equals 1, so c times x is just 9. So this simplifies into 5 plus 20 is 25 plus x is 31, equals 24 plus 2b plus 9. Right? So we're going to subtract 24, and we're going to subtract 9. So 31 minus 24, that's 7. And 7 minus 9, well that's negative 2. So negative 2 equals 2b, running out of space here, which means that b equals negative 1. Right? So let's plug those into our original statement. So a equals 6, So we'll have 6 over x plus b is negative 1. So we'll have negative 1 over x plus 1 plus c was 9. So we'll have 9 over x plus 1 squared. So how do we do this now? This is pretty basic. We can integrate this. We would do basically you just do the integral of that, dx, plus the integral of that, dx, plus the integral of that, dx. Well, this is just basic 1 over x, that's the integral of that is ln of x. The integral of this would be ln of x plus 1, and the integral of this, well, we'd have to do u substitution, but again, it's very basic antidifferentiation. So that's the big second part of partial fractions decomposition. And there is one more point. So you'll see this in our next video.